All right, we'll go ahead and get started. We'd like to thank all of you for coming out and joining us for this exciting webinar by AccelerEyes. We're anxious to get started and hope that this will be beneficial for you as we specifically focus on our product ArrayFire and also Fortran for the specific Fortran user. So without further ado, we'll go ahead and get started here. Again, if you have any questions, feel free to insert those into the chat box there by the participants window. So just to get started here, we of course are going to be discussing our product ArrayFire. And ArrayFire is a GPU software library. It's the world's most comprehensive GPU library. And it is especially for C, C++, Fortran, and Python users. It's productive and easy to use software, and it supports both CUDA and OpenCL devices. Just to give you a little bit more background about ArrayFire, ArrayFire complements all GPU code. So we've got this little graphic up here to help you understand that a little bit better. So it adds functionality to OpenACC directives. It helps you save time with programming raw CUDA or OpenCL code. And it helps you reduce time and code less in using it as a general GPU library. It's got hundreds more functions than the average GPU library you might find out there. So it's, as I mentioned earlier, it's the most comprehensive GPU library currently out there on the market. ArrayFire is easy to use. As you can see here, this is a very simple depiction that describes how ArrayFire uses fewer lines than Trust. So that's what we're trying to depict here in this simple graphic, is to show that ArrayFire, it requires fewer lines than Trust. So you code less and it decreases your time of programming. ArrayFire is fast. This is a very quick graphic here that also shows a comparison to Trust. And as we mentioned earlier, ArrayFire complements Trust. It adds more functionality and also provides faster speed. Also, I just wanted to point this out. We've had a lot of success with our customers using ArrayFire. We have lots of examples on our website. We encourage you to go to this link here at the AccelerEyes.com/case studies. And there you will see a variety of applications from industries across the spectrum and just about any vertical you can imagine where our customers are using ArrayFire to have success. So we'd encourage you to go take a look at those. There's some really exciting examples and case studies of people that are using ArrayFire every day to help speed up their applications and speed up their code. This is just a very brief introduction here. We'll be discussing more about how to actually get in and see the code relating to ArrayFire, and especially for Fortran users. But just wanted to show this this page here, which describes the various matrix types or the data types that you can use in ArrayFire, and it makes it very simple and easy to use when using the specific functions that you require for your application. As I mentioned earlier, ArrayFire has hundreds of functions. It's the most comprehensive GPU library currently in the market. Everything from reductions to convolutions to linear algebra, image processing, just about every function that is in demand right now currently in the market, ArrayFire supports. And we'll be getting into some more examples here later on during the webinar where you can learn more about how ArrayFire and specifically Fortran, ArrayFire Fortran can help you in your application. These are just a few slides here I wanted to fly by real quick, showing the speed that ArrayFire has. This is an example of a matrix multiply and a sum. As you can see, it's comparing ArrayFire to other products that might be out there, MKL, Eigen, IPP, and Armadillo. As you can see, ArrayFire's performance is significantly faster. Here's convolution, and also there's a cumulative sum and a sort function. So ArrayFire has plenty of speed. Now, just getting back to what I mentioned earlier, the whole package that you're getting with ArrayFire is a value proposition that eliminates the costs that are associated with software development. So you look at the little chart here, you can see that with porting and maintenance and the documentation, development, everything that you have to do, that can become a big pain. It takes a lot more time and increased costs for developing your application. With ArrayFire, we try to eliminate the pain involved in that process and make it faster and less expensive for you to be able to program, and so that you can work on the other facets of your business. So that is the value proposition. We want to make life easier for you and eliminate the pain with developing your code with GPUs. So that's our value proposition, and we're having a lot of customers experience success with ArrayFire. ArrayFire is easy to maintain. You can write your code once, and then you can let ArrayFire carry you through the coming hardware evolution. So we're constantly enhancing the functions and capabilities of ArrayFire, and with each new ArrayFire release, you can improve the speed of your code without any code modification. And ArrayFire, just to give you a little bit of background on ArrayFire licensing, we have a variety of options that you can dive into and help you get started. First off, there's a free version, and the free version is for 1 GPU, and it's a shared license, and it requires an internet connection. It's fully functional and it has full performance, but we do limit it to 1 GPU, and it requires the internet connection. There's also an ArrayFire developer version for 1 GPU. That's a dedicated license, and there is a fee attached to that. Also, there's a professional and enterprise version, also dedicated licenses, and we call that ArrayFire Pro. So I'd encourage you to go to our updated licensing page. It's at AccelerEyes.com/products/ArrayFire licensing. And we try to provide a robust number of versions and options for you so that you can select the one that would work best for your current needs. Here's just a quick quote I wanted to point out here of an example of a customer that's experiencing some fantastic results with ArrayFire. This was Dominic from Katsaris Investments, and as you can see, he was able to get a 50x speed up, rather impressive, with ArrayFire. And as you can see, he was able to save a lot of time and obtaining the optimization that he wanted without having to go through the pain as we described earlier. He was able to use ArrayFire and get the results that he wanted fast, and that is the model that we want for our customers, and hundreds of our customers are experiencing similar results. So this is just one example of many of our customers that are having fantastic results with ArrayFire. All right, now we're going to move on to the part that a lot of you probably were especially interested in, and that is to dive into some ArrayFire Fortran examples. And to get started, before we jump into that, I'm going to have my colleague Pavan, he's one of our ArrayFire engineers. He's going to walk us through some of the code examples of ArrayFire Fortran. But before doing that, I wanted to actually take you to our ArrayFire Fortran page, which includes all of the documentation you're going to need to get started today if you wanted to. If you already have an ArrayFire license, you could jump on this page, AccelerEyes.com/ArrayFire/Fortran. So here we have the ArrayFire Fortran documentation page, and I would encourage you to hop on this page when you get a chance, and you can very easily walk through this, and it'll help you get started here right off the bat. You can see some of the basic points that we covered about what ArrayFire is and the benefits that it can have for your code. You can also go through the tutorials, which we highly recommend. That'll help you get started. And then, of course, if you go here to the Categories tab, you can browse the functionality currently available for ArrayFire Fortran. So I would highly recommend that you go through and browse through this page, as you can with all of our products. We have full documentation on all of our products on our website, and I would encourage you to take a look at this, and it would be a huge facilitator for you to get started on your ArrayFire Fortran programming.
Okay, hi, this is Pavan from AccelerEyes. Let me begin by sharing the documentation once more. Okay. If you go to ArrayFire/Fortran and then go to the categories tab over there, you can see the list of functions that we support using the ArrayFire Fortran interface. This is our basic data type in Fortran that we use to represent an ArrayFire array that operates entirely on the GPU. Here you can see a simple code segment that is just transferring small matrix A onto the GPU array ARR. You can do a bunch of operations after that, like adding an element 1 to it and then doing a log and just getting it back to the host side matrix. As you can see, this is an example of how you can assign data from host to the array and get it back. But you can also create arrays using some of our random number generators or other constant matrix generators, like you can see here. The interface is very simple. You just declare your array that you want initially, and then you can use the function that you like and then generate the matrix of the size that you intend to use. For example, RandU generates the matrix of uniformly distributed numbers. Random generates the normally distributed random matrix, and so on and so forth. Generating the matrix is only useful if you can do some kind of operations on them. Like if you want to, you can do operations like transpose and then assign it to a second matrix, and then you have functions like sort over here, reorder, which is just reshaping the matrix and manipulating the dimensions on a given matrix. And then you have a bunch of mathematical operations over here doing addition, subtraction, and so on. And then relational operators which compare two matrices of the same size, or between a matrix and the scalar, as you can see here. You can generate a matrix and compare between two of them, or you can compare between a matrix and a scalar, as you can see here. And then we have a whole bunch of linear algebra functions. The most simplest of them are matrix multiply, which you can call using mathmul. In this particular code snippet, you can see a matrix A of size 20 by 25 is generated and multiplied by another matrix B of size 25 by 10. And matrix multiplication is as simple as saying mathmul of A comma B. You can go through other function names from the documentation and see each of them has a code snippet explaining how this function should be called. For example, over here you can see a particular function called eigen, which generates both eigenvalues and eigenvectors of a given matrix A. So, yeah, the page you need to have a look at if you want to find proper documentation is the categories tab after going through our Fortran documentation. You can also look at some of our examples, but these are slightly outdated. We plan to add a few, bunch of more examples in the next release. But I want to show you the very basic example of what you can do with ArrayFire. Initially, you declare all the variables that you want, and you populate the input host side matrix. This is just a diagonal matrix with non-zero elements along the diagonal and 0 elements on off diagonal. You can then take the matrix from the host to the GPU using just the equal operator, and then to just display, you can just call the function dis of m1, which will show you the matrix. I'll be running these examples once I go through each function over here. This function is just generating random number matrix, like I mentioned before, displaying that again. Simple transpose display that again. As you can see, display can also print out a message if you intend to. This is very useful for debugging purposes and so on. If you intend to display a matrix and you want to know where it is coming from and so on. You can do element-wise operations, negation, just do complex operations like this, and complex trigonometric operations like this, or linear algebra operations like this, which is being done using MATML. And then there is also reductions which you can do using min. This will just find the minimum value along each column of the matrix M2. You can either go through the examples list from here, or you can go to our ArrayFire download page and download ArrayFire and actually go through the examples from the actual distribution. So let me switch to the remote machine and show the examples and see how they run and how they perform. This is the same example that was shown from the website. Let's go to the console. We can do a simple make. This was already pre-built, so you can run the example using. Okay. As you can see, the original matrix A, which was diagonal matrix, is transferred to the GPU, and you can see the output over here. And then you can see a randomly generated matrix M2, and you can see and the transpose over here. And you can see that element, that result over here is the element-wise addition of the two previous matrices from here and here. For example, there's the element 1 and you're adding to 0.74 and getting the results here. And you can verify the rest of the results when you actually run them. You can also do negation on a single matrix and do and display them, and obviously sin square x plus cos square x is 1, so that's what you're seeing here. And this is the output of a simple matrix multiply. And this is the output of element-wise multiplication. This is one of the things that confuses a lot of people, so we want to make that clear. The star operator does element-wise operations in ArrayFire, whereas MATML does matrix multiplication. And min of M2, like I said, does element-wise reduction on the matrix, on the input matrix, and you can see the list minimum element on what do you call this of each column being printed over here. And we are then getting back M2 and just displaying the same result on the host. So let me get back to another example here. I think a lot of you will be interested in linear algebra functions. So there is an example called DLA.F95 in the Fortran example. You can go and have a look at it and see how various linear algebra functions are being called. Initially, to do these examples, we will need to generate some input matrices. So that's what we are doing with A and X0. Then almost all of our linear algebra functions are called in this way, where you can say call the function name and the outputs followed by the input. For LU decomposition, you have the lower triangular matrix, the upper triangular matrix, and the permutation matrix as outputs and the A as input. Once you call this function and get the outputs, you do the okay. We will check for accuracy later on, but this is how you do LU decomposition. For doing AccelerEyes decomposition, you need the input to be positive definite. So that is what you're doing here. you're converting matrix A into matrix C by adding A to A transpose and making the diagonal really large. So R is the lower triangular. R is a symmetrical method. For Cholesky decomposition, R times R transpose will be C. So all we need is just one output in this case. So that's what we have here. And then for solving linear systems, we just have one method called solve. Let me explain what's happening here. We just generated A and X naught using random numbers, and we just create a system using the initial matrices. And then we solve for x1 is equal to, A times x1 is equal to B, and then find the difference between x0 and x1 and see if the solve routine performed as expected or not. So many people ask us if we have different solve methods based on matrix inversion, based on least squares, or Cholesky decomposition, or LU decomposition, and so on. What we have internally does all of that, but we try to make it as simple as possible to the user, and internally we perform checks on input matrices and call the best algorithm possible. We also intend to make it easier, make it more customizable, so user can call a particular algorithm if he knows the type of the inputs already. But right now that is not available in Fortran yet, but we do plan to add that. So just to demonstrate, we are solving, since A was a general matrix, this will be solving using LU decomposition internally. This will be solving using Cholesky-based decomposition internally. And over here, you're just doing an inversion of the matrix A and just reconstructing, multiplying A with its inverse and seeing if it's close to identity. You can also do matrix power using calling a function called matpower. So here you're creating a cube of matrix A and then again finding the absolute error. Let us run this example and see how the error, how accurate these functions are and how they are performing. As you can see, we are using for the error measurement, we are using maximum of absolute differences, and even for single precision, these are very close to zero. You cannot see them at least up to 4 decimal places. So another important thing is indexing in Fortran. This is somewhat hard to do given that we don't. This is somewhat hard for us to do. We can't emulate similar native look of indexing in Fortran, but we do have functions called get and set, which will index part of the matrices and then display. As you can see, what this part is doing is getting I1 columns and I2 rows from A1 to temp, and this particular function is setting temp into I2 rows and I1 columns of A2. So essentially, what it is doing is it's taking a chunk of data from A1, doing the performing some kind of a reshape, and then assigning it into A2. We will see what's happening by running that indexing over here. Okay. So for 1D indexing, what temp was doing was taking elements 3 through 5 and then setting it from 1 to 3 in A2. So temp here is last 3 elements of A1 and then moving it to first 3 elements of A2. Similarly, over here, temp is this particular the upper right-hand quadrant of A1 and moving it to moving the first 2 columns into the middle column into the first column and the third column into the third column over here. So as you can see, we can do pretty complex operations using the get and set operations. We can over here you can see that we also do three-dimensional accesses on data also. So this example showcases how to benchmark some code segments in ArrayFire Fortran. So you generally just generate the data that you want, start the timer, and for a particular number of operations, just do the same repeat the same operation for a particular number of iterations, and then call a device sync. This is really important if you want to do benchmarks, but not really necessary if you're in real, in production code. So maybe have this as an optional thing that you want to do when you're doing benchmarking. This is necessary because all the kernel launches and all the CUDA calls are done asynchronously, and they do not, and they on, the execution does not stop until we explicitly ask it to, or the data is needed by some other function. So over here we are saying device sync, which will make sure all the matrix multipliers that we are performing on the top will be done. So over here we are converting we are taking the time taken, dividing it by the number of iterations, and multiplying by 1000 to get it into milliseconds. And here we are converting the time we have in milliseconds into gigaflops. Oh, this should have been gigaflops. Okay. So we're just displaying the time taken and gigaflops. So let's just build that example and run timer. So we are just benchmarking matrix multiply for matrix width of 2048 by 2048, and you can see it ran in 26 milliseconds and getting a performance of 655 gigaflops, which is pretty good for some of the older generation Tesla cards these are running on. And then finally, if you want, this is I think what most of you guys will be interested in, because in HPC situations you would want to run your code on multiple GPUs, and here is an example of how you can do a simple matrix vector operation across multiple GPUs. This is a long example. Just don't be overwhelmed by it. We just need to set. Most of it is boilerplate for doing the benchmark and setting up the initial parameters and so on. Here we are just getting the operations. The arguments from command line and using them to set up the benchmark. You're creating the input. The matrices that we need for performing the benchmark. We need the time taken on the CPU for reference, so we are using MKL to do the benchmark and setting it based on user input from command line. It defaults to 8, but I'll show you that. We'll talk about more about that when we do the actual benchmark. So then we will need to allocate arrays for the number of devices that we'll be using in this benchmark. So each GPU needs to have its own small segment of the code. So we generate devices for arrays for each device. In this part, what we're doing is cycling through all available GPUs and then saying, device set. What it does is it will select a particular GPU. Right now, this is 0 reference, so device set of 0 will select the first GPU, and device set of 1 will select the second GPU, and so on. Calls per GPU is work that you're doing on each particular GPU. So the amount of work may not be even across all GPUs. So we're just trying to find out what is the first column and last column that you want to transfer to a particular GPU. Over here, you're transferring the parts of the data from the host to the relevant GPU, and you're doing a device sync to make sure the data is all sent to the relevant GPUs. And then you're doing the actual benchmark over here, where you're starting the timer, doing the matrix multiply for the given data chunk on the particular GPU, and then getting it back, and then reconstructing the output on the host. So this may not be the most optimal way to do things, but this is simple enough to understand how a simple matrix vector multiplication can be split across multiple GPUs. And then once this is done, you're finally stopping the timer to verify what the performance is. Here we are displaying important information about the matrix width, the number of CPU threads used, the devices, number of GPU devices used, and so on. Okay, let's go back to the console and run the multi-GPU example. Let's run this with a matrix width of 4096, and then 2 GPUs and 4 threads. So this may take a while because we are running it for multiple iterations to make sure we are getting an accurate average time. As you can see, the CPU time is nearly 8 times slower than what CPU time taken on 4 threads is nearly 8 times slower than what 2 GPUs took. One thing you'll notice is scaling it down to 2 threads on the CPU does not affect the CPU time much. Yeah, as you can see, the number of CPU threads equal to 2 is the same performance for when there are 4 threads. Just to make sure that the parameter is being set properly, we'll just run it with 1 thread and see the actual performances. As you can see, the CPU time goes down from when using 1 thread to 2 threads, but then from then on it does not change much. So what we can see here is, even though this is a very highly parallel problem, the CPU is not scaling properly with the number of threads being used. That's not the same thing we can say about CPUs, but let's run with a single GPU, 2 GPU, and 3 GPUs and see what's happening here. So the time goes down from 1.47 milliseconds on a single GPU to 0.78 on 2 GPUs. And when you go to 3 GPUs, for this particular size, the amount of data may not be enough to saturate 3 GPUs, so you may not get 3x speed up. But we can scale up the data size and see how this performs. Yeah, as you can see, on 3 GPUs, it is actually slower than what you're getting on 2 GPUs. So there is some oversight and transferring the data to 3 GPUs. So this is something you'll have to keep in mind when using multiple GPU systems, just because you have multiple 3 GPUs does not mean you may want to use all 3 of them. But if you scale this up to larger numbers, say 10,000, and do 2 GPUs, okay, and then go to 3 GPUs now. As you can see, there is an improvement of about 30% improvement from using 2 GPUs to 3 GPUs. But this is not as much as you would expect when going from 2 to 3. So even as a matrix width of 10,000 is not saturating the operations that we're doing here, but there is definitely improvement when going from 2 to 3 GPUs, and ArrayFire is taking full benefit of all the GPU systems available. As you can see over here, you are launching the functions from a regular for or do or while loop, whatever you want to call this over here. But all the operations are still being done in parallel because, like I said, all the operations are launched asynchronously, and they only stop once you call once you call it device sync, or if you want to transfer the data from host to the from the GPU to the host over here. So everything is being launched asynchronously. It's not waiting for it to be done, and then it just once the jobs are launched, you just go to the point where you want to synchronize, and then all the functions will be running in parallel from that point on until they are synchronized. So I think that's it from our end when it comes to showcasing our examples. So I think we'll be switching to a Q&A session right now. So let's see what kind of questions we have from the users. A user is asking us what is essentially the difference between a free version and the pro version, and how are these different? What?
Sure, I can take that. So the big difference between the free version and the pro version is that the free one only supports 1 GPU, and it requires an internet connection. I think in the slides I mentioned that briefly, but if you go onto our licensing page, it's AccelerEyes.com/products/ArrayFire licensing. You will see the full description of the different versions of ArrayFire. The free version is fully functional, so you'll get the full performance, but it requires the internet connection because it's a shared license that's accessed off of our license server, and it only supports 1 GPU. The ArrayFire Pro is it has the most value out of all of the options because it does not require an internet connection. It starts out at 2 GPU support, so you have multi-GPU support with that ArrayFire Pro version. And it brings with it the extra linear algebra features among a few other advanced features. So by far, ArrayFire Pro has the greatest value as far as the full package of capability and functionality. The free version is nice maybe to get started and to get familiar with it, but after that we recommend that people move to the professional version to get even better speed ups and better performance. Hopefully that answered the question.
Okay, we have another user asking us if he can use the ArrayFire on his ATI card. Right now we have an alpha version for ArrayFire up on our website, but it's only available for C++. But we are planning to release an OpenCL version in the near future. So if you can email us at support@accelereyes.com, we'll keep you posted when this thing goes live. There is another customer asking us if they can deploy ArrayFire executables onto other machines. So I think that again boils down to a licensing deal which Scott can talk about.
Yes, we do have the ability to deploy ArrayFire executables. That's something that we would need to discuss. So it's basically based on volume and the number of executables that you plan on doing. And so we would need to have a discussion about that and understand what you wanted to ultimately do there with the executables. So if you could please contact me directly at sales@AccelerEyes.com. I would be happy to help answer that question more fully, and we can discuss that further. But there is the capability to do that.
Okay. There is a next question. There is a question about one of the examples that I talked about on multi-GPUs. And the user asks, how do I know my particular data size is good for multi-GPU support or not? Is there a minimum set size that where the multi-GPU code can become efficient? So this eventually boils down to the problem that you're working on, and more often than not, the problem even if the GPU is fast enough, the amount of data that is required to perform that to solve the problem may not be available on a single GPU. So that is one thing you want to look forward to. So it's just not the speed up that you're getting from multiple GPUs, but also the added memory capabilities. But other than that, you would have to do trial and errors just to figure this out and what a optimal set is. But this is just like any other MPI or multi-threaded code, where you need to figure out what the optimal set of what the optimal data size is for when you're using a multi-machine or multi-node implementation. So moving to the next question, how easy is it to integrate ArrayFire into my existing Fortran project? So it is fairly easy. You can create a particular special function where you call ArrayFire, where you can transfer the data from the host to the GPU using nothing more than an equal to sign, which will just do a memory copy from the host to the GPU, and then call the relevant GPU functions from the ArrayFire library. You can find the list on our website, a list of functions available on our website or through the ArrayFire distribution that you get. So once you have performed all the operations that you need, you can just assign it back to the host again and use the data, use the return data to use the return data in a different function and so on. So you can just pick out the slowest parts, the really slow parts of your code, and do a direct replacement with the ArrayFire equivalent, and you will not face too much of an overhead in doing so. So there is another user asking us about ArrayFire libs working on any folder in the computer for Windows. Currently we do not support the Fortran library on Windows. It's only for the Linux 64-bit systems. But we do plan to add the support in the future. The biggest problem for us right now is trying to figure out what kind of a compiler users are having. So if you guys can send send us an email at support@accelereyes.com with the compilers that you use and the support that you need. We'll factor that into our development process and make sure to add the support in the near future. But right now, we do not support Windows and Fortran, so that's a big deal. We will need to add the support, but we'll have to apologize for not having that support right now. Okay. So another user asked us how stuff compares to the PGI CUDA implementation for Fortran. So you have to remember that ArrayFire is a library, and the PGI CUDA implementation is sort of like a compiler and a CUDA extension for C++. ArrayFire works with PGI as well as Fortran, but you may need to do some. You may need a special library from us to work with PGI. So coming to the actual differences between the CUDA implementation of PGI and ArrayFire is that they can complement each other because they are two different things. ArrayFire is a library, and PGI CUDA implementation is just a compiler, like we said. The learning curve for ArrayFire is much smaller because it is like any other library that you may have used in the past, like MKL or other BLAS and LAPACK libraries. You don't need to know CUDA to work with ArrayFire. That's a big plus for some of our customers. And another thing is we have a lot of engineers working on this hand tuning the performance of the CUDA, the backend CUDA code. So any benefits that you may get from writing handwritten CUDA code in Fortran may not actually perform that better than ArrayFire. So you'll save a lot of time when just going ahead with ArrayFire rather than PGI, if you're not already familiar with it. We suggest you go through our case studies and our forums and our documentation to see how ArrayFire can be useful for you in this regard. So I think that was one of the last questions asked. We'll be waiting for another couple of minutes to see if any of the users have unanswered questions, but if not, I think we'll be done for the day.
Okay, this is Scott here at Pavant. Thank you very much. I'd like to thank everybody for joining us on the webinar. And if you have any other questions, feel free to let us know. You can email me at sales@AccelerEyes.com. Again, we thank you for joining us and hope that you'll be able to have success in GPU computing with our products. Thank you very much and goodbye.